Space is vast, it's also mostly empty, but this emptiness is deceptive. But it's not just emptiness out there. There's more to the universe than meets the eye. There's something else, something we can't see, something mysterious and elusive. We call it dark matter. This enigmatic substance is a fundamental part of our universe. Dark matter is a strange substance. It doesn't emit light, it doesn't reflect light, it doesn't interact with electromagnetic forces. We can't see it directly. It's invisible to our eyes and our instruments. So how do we know it's there? How can we be sure of its existence? We know it's there because of its gravity. Its gravitational pull affects the movement of galaxies and stars. Gravity is the force that pulls things together. It's a fundamental force of nature. It's why apples fall from trees and why planets orbit stars. It's the glue that holds the universe together. Dark matter has gravity too. It influences the structure and behavior of galaxies. In fact, it has a lot of gravity. Its gravitational force is immense, more gravity than all the stars and planets we can see combined. It's a dominant force in the cosmos. Scientists estimate that dark matter makes up about 85% of the matter in the universe. This means it's a crucial component of our cosmic makeup. That means that everything we can see, all the stars and planets and galaxies, makes up only a tiny fraction of what's really out there. The vast majority remains unseen, hidden in the dark. The story of dark matter begins in the 1930s, a time when the universe was still largely a mystery to us, with a Swiss astronomer named Fritz Zwicky, a pioneer in the field of astrophysics. Zwicky was studying the Coma cluster, a massive group of galaxies held together by gravity. He noticed something odd, something that defied the known laws of physics. The galaxies in the Coma cluster were moving too fast, far faster than they should have been. They were moving so fast that they should have flown apart long ago, but they hadn't. They remained bound together. Something was holding them together, something with a lot of gravity, but it was invisible and undetectable by any means available at the time. Zwicky called this mysterious substance Dunkle Materie, German for dark matter. It was a revolutionary idea. At first, most scientists didn't believe him. They were skeptical of this unseen force. They thought there must be some other explanation for the strange movements of the galaxies, perhaps an error in measurement or an unknown variable. But then, in the 1970s, another astronomer named Vera Rubin made a similar discovery, reigniting interest in Zwicky's theory. Rubin was studying the rotation of spiral galaxies, focusing on the speed at which stars orbited the galactic center. She found that the stars in these galaxies were also moving too fast, much like the galaxies in the Coma cluster. They should have been flung out into space, but they weren't. They stayed in their orbits. Again, something invisible seemed to be holding them together, an unseen force that defied conventional understanding of gravity. Imagine a group of children spinning around on a merry-go-round. The faster the merry-go-round spins, the harder it is for the children to hold on. If the merry-go-round spins too fast, the children will fly off. Galaxies are kind of like merry-go-rounds. The stars in a galaxy are like the children, and the gravity of the galaxy is what holds them together. Just like with the merry-go-round, if the stars in a galaxy are moving too fast, they should fly off into space. But they don't, and that's where dark matter comes in. Dark matter provides the extra gravity that galaxies need to hold onto their stars. It's like an invisible glue that holds the universe together. So, we can't see dark matter, but we can see its effects. We see it in the way galaxies move. We see it in the way light bends around massive objects, and we see it in the cosmic microwave background radiation, the afterglow of the Big Bang. The cosmic microwave background radiation is a faint glow of light that fills the entire universe. It's a snapshot of the universe as it was just 380,000 years after the Big Bang. By studying the patterns in this radiation, scientists can learn about the early universe. These patterns tell us that dark matter was present in the early universe. In fact, it was much more abundant than ordinary matter. Without dark matter, galaxies would not have had enough time to form. Section 5. The Bullet Cluster, a Smokin Gun. One of the most compelling pieces of evidence for dark matter comes from a cluster of galaxies called the Bullet Cluster. This cluster has provided astronomers with a unique opportunity to study the mysterious substance that makes up most of the universe's mass. The Bullet Cluster is actually two clusters of galaxies that have collided with each other. This cosmic collision has created a fascinating scenario for scientists to analyze. When the clusters collided, the gas in the clusters heated up and emitted X-rays. These X-rays are crucial because they allow astronomers to see the otherwise invisible interactions happening in space. By observing these X-rays, astronomers were able to map the distribution of the ordinary matter in the bullet cluster. This mapping process is essential for understanding the structure and behavior of the cluster. But here's the weird part. The gravity of the bullet cluster doesn't match the distribution of the ordinary matter. This discrepancy has puzzled scientists and led them to investigate further. The strongest gravity is located in regions where there is very little ordinary matter. This unusual finding suggests that something else must be contributing to the gravitational pull. This is exactly what we would expect if dark matter were present. Dark matter, though invisible, exerts a gravitational force that affects the movement and distribution of galaxies. The bullet cluster is like a cosmic crime scene. By studying it, astronomers can piece together clues about the nature of dark matter and its role in the universe. The separation of dark matter and normal matter is like the smoking gun that tells us dark matter must be real. This evidence is a crucial piece in the puzzle of understanding the cosmos. Section 6. Gravitational lensing, dark matter's telltale distortion. Imagine a bowling ball on a trampoline. The bowling ball will create a dent in the trampoline. If you roll a marble across the trampoline, its path will be bent by the dent. This is similar to what happens when light passes by a massive object. The gravity of the massive object bends the path of the light just like the bowling ball bends the path of the marble. This bending of light is called gravitational lensing. Astronomers have observed gravitational lensing around galaxies and clusters of galaxies. The amount of lensing is much greater than can be explained by the visible matter in these objects. This tells us that there must be a lot of invisible matter present, matter that we can't see, but that we can detect through its gravity. Section 7. WIMPs and Axions, the hunt for dark matter particles. So, what is dark matter made of? We don't know for sure, but scientists have some ideas. One possibility is that dark matter is made up of particles called WIMPs, which stands for weakly interacting massive particles. WIMPs are hypothetical particles that interact very weakly with ordinary matter. This makes them very difficult to detect. Another possibility is that dark matter is made up of particles called axions. Axions are also hypothetical particles, but they are much lighter than WIMPs. Scientists are currently conducting experiments all over the world to try to detect dark matter particles. These experiments involve building incredibly sensitive detectors and placing them deep underground, where they are shielded from cosmic rays. Section 8. The cosmic web. Dark matter's role in large-scale structure. Dark matter isn't just scattered randomly throughout the universe, it forms a vast, interconnected network called the cosmic web. This web is made up of filaments and clumps of dark matter with vast voids in between. The cosmic web is the scaffolding upon which galaxies are built. The gravity of dark matter pulls ordinary matter together, forming the seeds of galaxies. Over time, these seeds grow into the majestic galaxies we see today. Without dark matter, galaxies would not have formed as early or as quickly as they did. Imagine a spider web. The threads of the web are like the filaments of dark matter. The drops of dew that cling to the threads are like the galaxies. The web provides the structure and the dewdrops collect where the threads intersect. Section 9. Dark matter and the fate of the universe. The fate of the universe is a question that has fascinated astronomers for centuries. Will the universe continue to expand forever, or will it eventually collapse in on itself in a big crunch? The answer to this question depends on the amount of matter and energy in the universe. If there is enough matter, its gravity will eventually halt the expansion of the universe and cause it to collapse. If there is not enough matter, the universe will continue to expand forever. Dark matter plays a crucial role in this cosmic equation. Because it makes up the vast majority of the matter in the universe, it exerts a powerful gravitational pull. The more dark matter there is, the more likely it is that the universe will eventually collapse. Section 10. Unanswered questions. The mysteries of dark matter persist. Despite decades of research, dark matter remains one of the biggest mysteries in astrophysics. We still don't know what it's made of, we don't know how it interacts with itself, and we don't know its role in the evolution of the universe. Some scientists have proposed alternative theories of gravity to explain the observations that we attribute to dark matter. These theories suggest that our understanding of gravity is incomplete and that we don't need to invoke dark matter to explain the motions of stars and galaxies. However, these alternative theories face their own challenges. So far, none of them have been able to explain all of the observations that support the existence of dark matter. Section 11. The future of dark matter research. The search for dark matter is one of the most exciting and challenging areas of research in astrophysics today. Scientists are using a variety of techniques to try to unlock the secrets of this mysterious substance. New telescopes and detectors are being built that will be even more sensitive than current instruments. These instruments will allow us to study the distribution and properties of dark matter in greater detail than ever before. Theoretical physicists are developing new models of dark matter and its interactions. These models will help to guide future experiments and observations. The study of dark matter is a journey into the unknown. It's a search for answers to some of the most fundamental questions about the universe we live in. What is the universe made of? How did it begin? And what is its ultimate fate?